Alright, in this video we're going to talk about solving triangles, and specifically we're going to talk about using the law of sines, and then even more specifically what's called the ambiguous case within the law of sines. So just in general, when we say that we want to solve a triangle, which is our focus here, what's meant by that is that we're going to be given three pieces of the triangle, and then we're asked to find the remaining three pieces. By pieces, of course, we mean sides and angles. So we're going to be given some combination of three of the sides and angles of the triangle and asked to find the pieces that we do not know. When asked to solve a triangle, you have several options. You have what many of you are familiar with as SOHCAHTOA, sine, cosine, and tangent, which we like. You should have memorized your special right triangles, your 30, 60, 90, and your 45, 45, 90 triangle. And then, of course, there's the Pythagorean theorem. Now, these three things that we've just mentioned, of course, those only work if the triangle that we're given is a right triangle, which would mean that one of the three pieces that was given to us was that one of the angles was 90 degrees. If that's not part of the given information, then we're left with these two options. And that would mean that the triangle, we don't at least know that the right triangle, or that the triangle is a right triangle. Maybe it will turn out that it will be, but we're not given that one of the angles is a right angle to start. And just because it's good to know, a triangle that's not a right triangle is called an oblique triangle. So you have right triangles and you have oblique triangles. If the triangle you're solving is right, you have basic trigonometry, special right triangles, or Pythagorean theorem. If you don't yet know that the triangle you're solving is a right triangle, then you have the law of sines and the law of cosines. Now what's interesting is you can use the law of sines and cosines for right triangles. So these two at the bottom, these work for any triangle. These three at the top, those only work if we're given that it's a right triangle. So you must know that to use the three original ones. Now these are the options you have, the tools at your disposal to solve a triangle. Over here, what I've listed is the options for what the given information could be. Like we said, we're going to be given three pieces of the triangle. And the three pieces could be three sides, two sides and the angle in between them, two angles and the side in between them, two angles and the side not in between them, three angles, or two sides and the angle not in between those two sides. Now hopefully we remember our geometry. These are just all the possibilities for a group of three of the six things. And again, if we remember our geometry, only these first four are allowed to prove that two triangles are congruent. Meaning, given any of these four options of three pieces of given information, you will always get only one triangle. Always only, sorry, my handwriting with this is not great, one triangle. That's why those work in geometry to prove that two triangles are congruent, because given those three pieces, whatever they might be, but given some combination of these three pieces, there's always only one possible triangle. Now again, hopefully we remember our geometry. Angle, angle, angle does not work to prove two triangles are congruent. The reason for that is there's no way for us to figure out from just the angles how big the sides are. We have similar triangles where the angles are all the same, but the sides are different lengths. So you cannot solve a triangle given just three angles. There's no way to know how big the sides are. And it's this this final option here of three given pieces, side-side angle, that we're interested in today. Again, remembering our geometry, this used to be bad. If we spell it backwards, it is bad. Many of you probably remember that that's how you remember that this does not work for proving triangles congruent. Now what we have to recognize is this word always from up above. Given these four original possibilities, side, 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 angle, or angle, angle, side, there's always just one triangle. But with side, side, angle, sometimes there's one triangle, sometimes there's more than one triangle, and sometimes there's no triangle at all. That's why we use the word ambiguous. We're not quite sure yet what's going to happen. We have to dive deeper into the information to figure it out. And that's what we're going to talk about today. What happens if given a side-side angle triangle? So here are the possibilities if given a side-side angle triangle. Now, we must focus on what it says at the top. We're focusing again on side-side angle, and we're focusing on being given side little a, we use little letters to represent side lengths here, side little b, and then angle alpha. Just so we know, alpha is kind of like a fish. That's alpha. And then we're supposed to find the remaining two angles, beta, gamma, and then side little c. And so given two sides and an angle, and it's important that we notice this is side-side angle. We are not talking here about side, angle, side. That's not what we're talking about here. This is separate. Separate. Side-side angle, only one triangle is possible. Side-side angle is what we're talking about here. Four possibilities. Side, angle, side, from geometry, remember, that's good. That proves our triangle is congruent. Only one possible triangle. So we notice in each of these pictures where we're given A, B, and alpha, alpha is not the angle between A and B. Alpha is over here in the corner by itself. And so the four options are no triangle, one oblique triangle, one right triangle, or two triangles. No triangle, that happens when A is less than H. And we're going to talk about what H is in a minute and how to find it, but it's the height of the triangle. And this should make sense. I've included this little arc here so that we can imagine this side length A, which we can't change because we're given the length of that side, and we can't change alpha because we're given that, and we can't change B, but I'm allowed to change this angle here at the top, so I can imagine swinging this side around, and it's not going to meet this third side down here. It would meet right here, but then I've changed the length of B. So that would be no triangle possible here, no triangle possible. If A is less than H, I have no triangle possible. It's important that we notice the relationship here. A is the side across from the given angle alpha. In your homework, you're probably going to have different letters than this. So it's important that we recognize that relationship. What we're comparing is A, the side across from the angle that we know, to the height. And we haven't really yet talked about B in this case. Now, if we have one right triangle, that happens when A equals H. We can imagine from up here extending the length of A so that when we swing it around, it does hit this third side nicely here. Because again, I can't change this angle alpha. It's set. It is set already. And when that side A swings around and is the right length, then we get our triangle. We can then find our angle beta would be 90. We could find our angle gamma up here, and we could find this length, which in this picture is 1, 2, 3. So that's nice. And again, comparing A, which is the side across from the given angle alpha, to the height. Now in our third option, we're just going to compare A to B, the two sides. And A needs to be greater than or equal to B. Again, you must focus here on the fact that A is the one across from the given angle. That's the one that needs to be bigger than B. Or it could be equal to, and we'd have an isosceles triangle. But typically we're looking for A being bigger than B. And A is the one across from alpha. If the one given side that's across from the given angle is bigger than the other given side, we only have one oblique triangle. And this is what you're probably used to seeing when you first learned law of sines. Often people first learn law of sines and just use it for this one special case when there's only one oblique triangle possible, and then afterwards we come up and talk about these other three options. So the most interesting one, option 4, when we have two triangles. And that's when A is less than B, but also greater than H. We know that if A is less than H, we'll have no triangle. If it's equal to H, we'll have one right triangle. But if A is bigger than H, but also less than B, so we don't have this one, that's when we'll have two triangles. And we can see the way that this works out here. I've shown two triangles with the same side length A, same side length B, and then the same angle alpha down there. And what happens is we take this side length A and we rotate it over to get our second triangle. And we can see that. The same length A, swing it around and it will intersect that bottom line again. And it will definitely change the length of C, but C is not something I'm given, so I'm allowed to change that. I didn't change alpha, I didn't change A, I didn't change B, and I have two different triangles, with then two different gammas, C's, and betas. And so that's what we're most interested in here, is two different triangles. Now a lot of what we've talked about here is comparing A to H. Is A less than H? No triangle. Is A equal to H? One right triangle. Is A greater than H and less than B? Two triangles. Now if we look at our picture here, A and H, if I form a little right triangle here with the height, we know the height is perpendicular to that side, then the sine of alpha would equal opposite, which is H, over hypotenuse, which is B. And so B sine alpha, my alphas are not good here today, is equal to the height. So all of these times when they tell us to compare A to H, they're really telling us to compare A to B times the sine of alpha. A less than H is the same as saying A is less than B sine alpha. A equal to H, A equals B sine alpha. A greater than H, A greater than B sine alpha. And again, must focus on the fact that A is just the side across from the given angle. You're always going to be given one angle and two sides in a side-side angle situation. And so A is the side across from the given angle. B is the other side you're given. So it's B times the sine of alpha that gives us the H, and we're comparing A to that. Let's look at a couple examples here. Often in this type of problem, they don't give you a picture, and you have to draw it for yourself. And I would typically try to draw how those 4 examples were shown to us on the previous slide. I try to just draw a general triangle. Don't make anything special about it. Don't make it equilateral. Don't make it isosceles. Just a random triangle. And like they did in those ones that we were just looking at, I like to put the alpha down in this corner, and A needs to be across from it, and then B is one of the other sides. It doesn't matter where I put it. I'm just going to put it here to sort of follow the same pattern as what we just looked at. Now when I think about this, the first thing I want to check for is in those four possibilities, A being greater than B. That's the easiest one to see. I don't have to compare it to H at all. I don't need H. And here I can clearly tell that yes, A is in fact greater than B. So that tells me I should have one oblique non-right. Remember, when we say oblique, we mean non-right triangle. One oblique triangle. So that's easy. This is what I'm used to with law of sines. I can just put this together like a normal law of sines. And so law of sines tells me I'll have sine of 30 over 20 is equal to sine of beta, because beta would be across from B, over 16. And to get the degree measure for beta, the first thing I'll need to do is just multiply this 16 to the other side. So I have 16 sine 30 over 20 equals sine beta. Now I should just be able to type that into my calculator and take 16 times the sine of 30 and divide that by 20. When I do that, I get 0.4. And so 0.4 is equal to the sine of beta. Then if I know the sine of beta, I just need inverse sine to get beta. So inverse sine 0.4 is equal to beta. And my calculator again can tell me that that's 23.578 approximately. And this is in degrees. And so now I have beta. Beta is 23.578. Here's beta over here. Should be pretty straightforward to find gamma, my remaining angle. If you know two angles of a triangle, to find the third, just subtract from 180. So we have 180 minus, we had our original angle was 30, and now we just figured out this other angle was 23.578. And so again, we should just be able to calculate that. And according to what I got earlier, that's about 126.472. And that equals gamma. And so now we've found two of the missing pieces. We need to find the remaining missing piece. And so to do that, to find C, we can again use law of sines and just set that up with gamma. So the sine of 30 over 20, just like we did to start, would equal this time the sine of 126.472 all over little c. Now, a very important thing to point out here. When I'm doing law of sines this time, my law of sines is using one angle, one side, and another angle. I don't have to worry about another triangle. Anytime you do law of sines, you should always just double check. Wait, am I using side-side angle here? I might be introducing a second triangle, but I'm not because I'm using angle, angle, side. So I know I'm good. So always just double check, are you using side-side angle? Because sometimes people are not careful and you end up using a side-side angle when you don't need to. So as I work this out, I'll multiply c to the other side, and then multiply the other side by 20, and then divide by sine of 30, giving me that c is equal to 20 sine 126.472 divided by the sine of 30. And if you know your trigonometry, you should know the value of the sine of 30, but you'll have to put the rest of it in your calculator anyway. So we calculate, and we get C is about 32.1867. This whole problem started because we recognized I do have a side-side angle situation. I need to be careful about how many triangles I might have. Once I see that A is bigger than B, A again being the side across from the given angle, B being the other side, I know that I only have one triangle, so I just proceed with a simple law of sines. Let's look at another example. So again, I can see I'm given two sides and an angle. I need to be careful about possibly side-side angle. So I draw my triangle just to see what it looks like. And when I draw my triangle again, don't want to draw anything fancy. I don't want my shape to somehow influence my thinking for the problem. I'm again given that this is 30 and this is 16 here. Oops, that's a better 6. Well, not much better, but better. And now we've changed the value of A to 7. Last time we compared A to B, which told us that we only had one triangle. Here my A is definitely less than B, so I don't know that I have just one oblique triangle. I need to think about what else I might have. In that case, I need to think about H, the height of my triangle. And if we remember to find the height, we did the sine of 30 is equal to H over 16, because we've made a right triangle here in the middle now. And so 16 times the sine of 30 would be my height. If you know your trigonometry, you should know that that's 8 for the height. If you're not sure how I did that so quickly, just do it on your calculator. So 8 is the height, so that tells me, 7 is less than H. 7 is A. A is less than H. That means I have no triangle. So again, even though I drew a triangle, that triangle was just for my reference. I don't have a triangle because in real life, this side 7 here would be much, much shorter. Actually, let's... and if we think about that, that's not going to reach all the way down. It's just going to swing over here and not quite touch. So we won't have a triangle that would reach all the way to the bottom of my 30 degrees down here. So no triangle here, and I'm done with this one. Okay. First thing we did was we compared A to B. A was less than B, so we knew we had to go further in our comparisons. We compare A to H. A was less than H, no triangle. Let's charge on in our examples here. Same setup, given alpha, A and B, one angle, two sides, might be a side-side angle. Let's draw it and check it out. Picture just for my reference here. We've got 30 degrees down in this corner. We've got 10 as A, the side across from the given angle, and 16 as B, the other side. And there's nothing special about my triangle. I just prefer to always draw it in the same way. It helps me kind of have a pattern of what am I looking for here. First thing I compare, A is less than B. I don't have that first situation we looked at where we just have the one oblique triangle. I need to go further and see if we have any triangles at all, or maybe perhaps two. Since two of the three pieces here are the same, my problem's going to work out pretty similar here. I need to look at H, which will again be the same as it was in the last problem. sine of 30 is equal to h over 16. 8 is going to be my height, and in this case 10 is bigger than 8. So because A was less than B, but also A was greater than H, in this case we have two triangles. And so we need to carefully, very carefully work through how we would find our two triangles. And the two triangles starts exactly as if it were just one triangle. Okay? So now we know that there's two triangles, so I just basically start how I would have to with law of sines here. And so what I would have to do first is I would have to say sine of 30 over 10 is equal to sine of beta over 16. If I multiply 16 by both sides, or both sides by 16 to move that over here, I'll get 16 sine 30 over 10 is equal to the sine of beta. 16 times the sine of 30 over 10 gives me 0.8, so that's nice. We have chosen some nice numbers here. Equals the sine of beta. Inverse sine of 0.8 gives me about 53.13 degrees for beta. And so nothing's different here. We would have gotten to this point even if we hadn't checked for how many triangles we had. But because we now know that we have two triangles, I'm going to think about my second triangle now. And so in my second triangle, I'm just going to kind of divide the page here for my second triangle. I know from the pictures we looked at before, my second triangle is going to look very skinny and obtuse here. And I'm still going to have 10 here, I'm still going to have 16 here, and I'm still going to have 30 down in that corner. And again, if we remember what happened when we first looked at these possibilities, is that there is the possibility of this other triangle here. And that's not a very good drawing. Let's make that a little bit better. Let's erase that. Gone. Let's make that better. A little better. So now this side here would also be 10, and you can kind of see the two different triangles here. And what's super interesting here is that we have actually an isosceles triangle being formed. And so this side is 10, this side is 10, and so I have one possibility, which I'm doing over here, of the larger triangle, one possibility of the smaller triangle, and then sort of the in-between is this triangle here. I'll draw it again over on this side and we can see what's happening. So you can see there's the two different triangles that we're working with here and creating an isosceles triangle in the middle. Now this 53 that we found, that 53 goes here. I'm going to call that beta 1. Same over here. That's beta 1. But because these two sides are both 10, we have an isosceles triangle. And so this little guy is also approximately 53. So then to find the one next to it, I just need to subtract from 180. And that'll give me beta, what I'm going to call beta 2, which goes in that little corner next to the 30. So 180 minus my 53.13, that equals beta 2. And 180 minus 53.13 is 126.87. So now I have two angles in each of the separate triangles. I hope we can follow and see the two different triangles here. We've got this skinny little guy over here, and now we have the larger version over here. And so now we're just going to, from this point on, we're just going to solve each triangle individually. Once we know that there are two triangles, by comparing A to H and seeing that A is less than B but bigger than H, I jump into my law of sines like I normally would to find my second angle. But then because I know there's a second triangle, I subtract that angle from 180 to get beta in the second triangle. Then I just divide it up and I solve each triangle separately. That's why I've drawn this vertical line through the page here to show that they're going to be totally separate. And then I just go from here. Well, now in each triangle I have two angles. So to find the third, just subtract both of those from 180. 180 minus 30 minus 53, my 3's are bad, 0.13, and that gives us an angle of 96.87, and that's going to equal our gamma in triangle 1, which would be this large angle up here, all the way across. That's going to be gamma 1. Same thing over here, but now we're going to find gamma 2, this little tiny guy right here, up in the top right. That'll be gamma 2. And so now we'll do 180 minus, well, we still have an angle of 30, but now instead of subtracting the 53, we're subtracting 126.87. So 180 minus 30 minus 126.87, that's 23.13 for gamma 2. And it should make sense when you get these numbers, you should recognize gamma 1 should be a much bigger angle than gamma 2 from looking at my picture. Also, beta 2 should be obtuse from looking at my picture. Even though I never want to judge off my picture what's happening, I know because of what we talked about, swinging this given side A over, one of these has to be an obtuse triangle. It has to be. And so I have that and I feel confident in my answer. Last thing to find in each is simply side C over here, and now this little tiny side C over here. To do that, we'll just do law of sines again. Sine of 30 over 10 is equal to sine 23.13 over little c. Work that out, solve it, and we get, and this is C2 of course because we're solving in the second triangle, and we'll get C2 is about 7.856. Similar over here, almost the same. Sine of 30 over 10 equals sine of 96.87 over C1. Only difference between the two is what my angle gamma was in each one. And that will of course change the answer. C1 should be much larger, and it is. If you work that out for C1 you get about 19.856. This is the problem that gives us the most trouble with these side-side angles because there's two triangles. But hopefully we can see that it's not that different. First thing I do when I'm given a side-side angle problem is I compare A to B, A being the one across from the given angle, cross. If A is less than B, then I go ahead and I compare A to the height. If A is now less than the height, then I have two triangles. Start with regular law of sine to find that second angle. Once you have that second angle, subtract just that angle from 180 to get the second angle in the second triangle. And then just go from there. I like to draw another triangle so that I can kind of see what's happening. Once you've gotten that second angle in each triangle, then you're just solving each triangle totally individually because they are separate triangles. Okay, let's look at a couple more. All right, same thing. Here we're given an angle and two sides, and so I want to draw a picture because I need to know what's the relationship between these things. And sometimes we're scared in this particular problem because, oh no, they've changed the letters on me. So what? I'm going to draw the exact same picture. Random, non-special triangle. I'm going to put my angle down here because I like to. And here I have to be careful, okay, which side goes over here? Well, because they gave me beta for the angle, B is the one that goes across from that. Some books would use a capital B instead of a beta. A lot of times, though, you will see a Greek letter for the angle, but the relationship still holds. Beta is across from B, or capital B is across from B. So here's my 6, and that was going to be a B and not a 6, and that's a 6. And then previously I was putting C on the bottom, but now because I want the relationships to still be the same, I'm going to put C over here. And so then I can do what I've been doing, compare this side to this side first. 6 is less than 10, so I know I might have two triangles or I might have no triangle. So I need to compare to the height. And here we've changed the numbers a little bit, so we're going to need to find our height again. So my height would be sine of 33 is equal to h over 10. Multiply that out. Multiply sine of 33 by 10, and we get an h height of about 5.446, which tells me I've got two triangles because A is bigger than the height. And so that means the height, if I had the 6 over here, it would work, or I could rotate that over and it would hit again here. So my height is less than A, so I now have two triangles. And now it's our job to solve each of the two triangles. We'll proceed exactly like we did before. And the first thing that we do is just do regular law of sines as if we didn't even know we had two triangles yet. So sine 33 over 6 is equal to the sine of beta over 10. And so the most important thing I want us to get out of this example is that the letters themselves don't matter. Just be careful with how you set up the triangle. Here's the given angle. Here's the side I know that's across from it. Here's the other side I'm given. I kind of like to always draw my triangle in the same setup, just because it makes it easier and because it doesn't matter how I set my triangle up. Even if your book gives it to you in a different arrangement, if they put the 10 down here, just move it. It's okay. It doesn't matter. The picture's probably not to scale anyway. Mine never is. So it's all about which angle is across from which side is across from the given angle. That's what's important here. So we've recognized there's two triangles. We're trying to find our beta, and really we're trying to find our beta 1 here. When I work this out and I find beta 1, or actually, I'm sorry, that should not be a beta. I'm sitting here talking about how the letters don't matter when they do right here. So the letters don't matter in the setup of the triangle, but they do matter because they do have names. So when I solve here, I'm not solving for beta, I'm solving for gamma, because gamma should be across from C. So here's my gamma 1. And so as I solve that for gamma, which is the same as how I would solve it for beta, I get that 65.194 is equal to gamma 1. Now again, that's gamma 1. I know there's a second triangle. And so in my second triangle, which will be an obtuse triangle, gamma 2, which will be right down here, should equal 180 minus what I just found, which was 65.194. And so when I do that subtraction to get my gamma 2, I get 114.806. And now again, I have two separate triangles, and I'm just going to proceed with each of them separately. In this triangle over here on the right, I still know that this is 33, I still know that this is 6, and that this is 10. It's just that my gamma is different. In the first triangle, my gamma is 65. In the second one, it's 114. And like we said in the last one of them should always be obtuse. Typically, it's the second one that you find. It will always be the second one that you find, actually. Okay, so then we go from there. Easiest thing to find next is the missing angle, which in this case, because we were given beta, and we now have found gamma in each triangle, would be alpha. So alpha for each of these, we would take 180 and subtract what we were given, as well as what we just found. $65.194. Lost my answer there. And when we get that, we get an alpha of 81.8062. But that's alpha 1. Same process over here on the left. Or, I don't know why I said left, it's clearly the right. 180 minus our given angle of 33, and our gamma 2, sorry, having trouble writing and I can't speak and write at the same time apparently. So then we subtract over in our second triangle and we get our second alpha, which this time would be 32.193, and that's alpha 2. And again, when we look at the picture, that should make sense. Alpha 1 is a much bigger angle than alpha 2. And then to find the remaining side, which in this case would be A, we just need to do regular law of sines. So over here, that's sine 33 over 6 would equal now sine of alpha 1, which is 81.8062 over A. And then over here, that would be sine of 33 over 6 equals sine 32.193 over A. This would be A2 and this one would be A1. When we work that out using our law of sine skills, we get 10.904 for A1 and 6.031 for A2. So hopefully that makes sense now how to do it when we do have the two triangles. We find that we have two triangles by comparing the side across from the given angle to the other side. Since the side across from the given angle is less than the other side, we know we must check for two triangles. Then we compare the side across from the given angle to the height, and if the side across from the given angle is bigger than the height, we have two triangles. Start your regular law of sines to get one extra angle, subtract that from 180 to get the second angle in the second triangle. And then solve each one using law of sines like you normally would. One last really quick example, I think. Now when I look at this given information, I notice something right away. It's different. Two angles are given to me. I have either an angle side angle or an angle angle side. Either way, I know I don't need to check for two triangles. I just need to solve regular law of sines. So I'm not going to go through that, I just wanted to point that out. Maybe we'll look at the triangle here real quick. Draw my standard triangle, throw in here one angle of 50, gamma is 20, and then A, which is across from the alpha, I should say, is 3, and so I can see it here. This is angle, angle, side, not side, side, angle, so I don't have to check for two triangles. Just solve it like you normally would with law of sines. And actually, you can really quickly now find the third angle, and then that will be helpful. So, only have to check for the two triangles if it's side, side, angle, not if it's anything else. Okay. Just wanted to mention that here. Sometimes we do this side, side, angle stuff, and then we start always checking for two triangles. Only if it's side, side, angle. If it's side, 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 angle, angle, side, angle, always going to be one triangle. And then just to review here are our four cases that we can have if it's side, side, angle. Compare the side that's across from the angle to the height. If it's less than the height, you have no triangle. But really, the first thing you should compare is, and this is the one that you should look for first, is A bigger than or equal to B? This is the one that you should check for first because you don't even have to check for the height. So you just right away, okay, what's A compared to B? A being the one across from the given angle. If A is bigger than or equal to B, you know there's only one triangle, just go ahead and solve it. If A equals H, it's a right triangle, and then you can use Pythagorean theorem or special right triangles or regular sine, cosine, and tangent. You don't have to do law of sines and cosines, so that's nice too. It's this one here that really gets us. First, we've compared that A is not bigger than or equal to B, so that's why we're down here. Then we compare it to the height, and it's A is less than the height. We have two triangles. Start solving the first one like you normally would, just like you would this one when you only have one, to find that angle beta, the second angle you can find, or I guess the first angle that you can find, the second angle in the triangle. And then once you know that first angle beta, then subtract that from 180 to get the second angle beta. Then solve the two triangles as if they were totally separate. Once you get this angle beta, these two triangles no longer have anything to do with each other. You're just solving them separately. All right, hope that helps.